Isaac Newton has been regarded by many scientists as the greatest scientist of all time. This is because one of his most significant contributions was expressing the physical behavior of nature through laws. And how do Newton's laws work? Newton drew upon the knowledge of various individuals to formulate Newton's laws. Thales of Miletus had already made significant contributions to mathematics and astronomy. Many centuries later, Galileo Galilei observed both the motion of celestial bodies and objects here on Earth. Through experimentation, he discovered that the velocity at which an object falls does not depend on its weight. He also wrote about how the Earth revolves around the Sun, and not the other way around. Subsequently, Johannes Kepler provided a highly precise mathematical description of the planet's orbits. But Newton's great achievement was taking the knowledge of Galileo and Kepler, and through discussions with Huygens, Leibniz, Halley, and especially Robert Hooke, formulating laws that explained the motion of celestial bodies, as well as the movement of any other object, and even the mechanics of machines along the way. And it all began because Hooke asked Newton to use his mathematical skills to explain the shapes of celestial orbits, such as the moon's orbit around the Earth. One day, Newton was sitting in the countryside, pondering the problem Hooke had presented to him when he saw an apple fall. He wondered, why doesn't the apple go sideways or upwards? This led him to ask himself, could it be that the same force pulling the apple down is what keeps the moon in its orbit? Thus, he contemplated the famous law of universal gravitation, which we will discuss further later on. So first, I will talk to you about Newton's 3 laws of motion. Newton's first law, also known as the law of inertia, tells us that every object continues in its state of rest or uniform motion in a straight line unless compelled to change its state by impressed forces acting on it. This means that if an object is at rest, it will remain at rest unless acted upon by a force, or if the object is in motion, it will continue moving in a straight line unless an external force changes its trajectory. For example, when we push a toy car, it moves in a straight line for a while, but eventually comes to a stop because there is a force pushing it downward and creating friction, which slows it down. And what about curved trajectories? It's a similar concept. For example, if you apply a force to a ball but it is attached to a thin string, there is a force that pulls the ball outward and another force that keeps it close to your hand. Instead of following a straight line, the ball follows a circular orbit. This is similar to what happens with the moon's orbit. The Earth must exert an attractive force because if the string were to break, the ball would fly off in a straight line, and the same would happen with the moon if the Earth suddenly disappeared. The second law of Newton, also known as the fundamental law of dynamics, states that the change of motion of an object is directly proportional to the impressed force and occurs in the direction in which that force is applied. What it wants to tell us is that the greater the force applied to an object, the greater the acceleration will be. For example, when we push a heavy object, if the object is at rest, meaning it has zero acceleration, we can set it in motion by exerting a force on it that overcomes inertia and imparts a specific acceleration. In other words, the trajectory is the result of the magnitude of all the forces acting on the object. This is expressed in the formula, force equals mass times acceleration. The third law of Newton, or the principle of action and reaction, states that for every action, there is always an equal and opposite reaction. In other words, if you push something, that something pushes back on you. Let's imagine that you and your friend, who weighs the same as you, are wearing roller skates, which reduces friction. If you apply a force to him, not only will he move, but you will also move. The force produces different accelerations depending on the masses of the bodies. So, if your friend is much heavier than you, guess who will move more? It is clear that these laws apply to objects that touch, pull, and push each other. And how is the law applied to apples and planets that are separate? Well, Newton determined that gravity was also a force. However, this force acts at a distance, and its behavior can be described by the law of universal gravitation. The force exerted by a point particle on another is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. That's correct. In other words, the greater the mass of an object, the more it will attract others, and the farther apart they are, the less they will attract each other. The combination of these 4 laws has allowed the construction of all kinds of machines, including the prediction of the arrival of comets, and has even enabled the building of vehicles that have taken humans to the moon. So later on, Albert Einstein would find the limitations of these laws and, of course, propose a new way of understanding, among other things, gravity. However, Einstein's theories would not be possible without Newton's laws, because as Newton himself said, "If I have seen further, it is by standing on the shoulders of giants." If you enjoyed this video, give it a like, share it, and subscribe to the channel. If you would like us to discuss a specific topic, please comment.